Hello, good people. Welcome to this episode. So, as promised in the previous video, this is about how to implement simple univariate linear regression models in PyTorch. And by being simple and univariate means that we are trying to let a model learn the linear relationship between a dependent and an independent variable. And I'm going to explain all that. I'm also going to keep the mathematics out of this video because I believe we are programmers and we understand things better when we implement them directly in code. So I'm going to write code to explain the mathematics behind how linear regression models work. Okay, so let's start off by importing torch, and I'm going to import numpy as np. I'm also going to import sys, and I'm going to import matplotlib.pyplot as plt, and then matplotlib inline to have inline graphs plotted for me. So I'm waiting for Collapse to finish its magic and then we can start. Okay, so a simple linear regression model is able to learn linear relationships between a dependent variable and an independent variable. A dependent variable is basically a variable whose value depends on another. Now, to be able to implement this model, I'm going to generate some artificial data set. And then in the next episode, when we are dealing with multivariates, I'm going to use a proper data set out there so that we can see how things work with different scenarios. Okay. So because this data set I'm going to generate is artificial, the relationship is going to be perfectly linear, but that's okay. For now, I want it to be very simple for you to understand. And so I'm going to create two tensors. The first one I'm going to call x, which is the independent variable. And that is going to be a tensor that I'm building out of a numpy array. And what I'm going to do here is I'm basically going to generate numbers between -20 and 20. And then the data type is going to be np.float 32. Take note of the fact that I am setting the data type on the numpy array, and the tensor, the PyTorch tensor, is going to inherit that data type. Okay, and then I'm going to create my y, which is the dependent vector whose values depends on the values in the x vector, and the relationship between them is x times 9 divided by 5, which is also equal to 1.8 plus 32. Now, I'm not going to tell you what this relationship tries to model in the real world. After we have implemented and tested it out, I will tell you what this model actually does, and then you get to appreciate some of the beauty of the gradient descent algorithm and its ability to model simple and complex relationships that we have in real world data. Okay, so now I have created my x and y. The x is independent because that is the values, let's say, we have measured, and then the y's are the values that depends on x. Both x and y can be measured anyway. All right, now let's implement our linear regression model. As much as I'm teaching you deep learning, I also want to teach you good software engineering practices. That is why I mostly build my models using the object-oriented principles of Python. Of course, there is no requirement that we always have to implement our model as a class, but then I also want you to learn how to write proper code. That is why I do simultaneously teaching you OOP and also deep learning at the same time. So I'm going to create a class called linear regression, and Python classes inherit from the object-based class, and I'm going to define my constructor, and it's going to take the self parameter. Now what we are going to do here is, first of all, we need to, let me just put this here for starters. So first of all, we need to see the relationship between x and y, and because this artificial data set has been generated to be perfectly linear, we know that the relationship between x and y is similar to the relationship between the x and y axis of the Cartesian plane when you plot a straight line. And what defines the relationship is m, which is the gradient of the line, and b, which is the intercept on the y-axis. So usually you see this formula, y equals ms plus b, or people also call it c. Okay, so in our case, our m is 1.8, which is also 9 divided by 5, and then our intercept on the y-axis is 32. So the objective here is to create the model and train it to be able to predict values that are as close as possible to the m and then the b. So in our class, we are going to use m to represent the gradient, the gradient of the line, and then we are going to use b to represent the intercept on the y-axis. And because gradient descent is going to be able to figure out these values regardless of where we start from, we are going to start by assuming that our gradient and our intercept on the y-axis are both zeros. So I'm going to say self.m is equal to torch.tensor. I'm going to create a tensor of type 0 with value 0, and then I'll say data type is equal to torch.float 32. So you see how similar the PyTorch APIs are to NumPy. You can see that D type, and then we also have D type, and then say NP float 32, and then torch float 32. Now this is the point where we are applying what we learned about in the previous video, which is how to indicate that you want the gradient to be calculated for you. So I'm going to say requires grad is equal to true. Why are we setting requires grad is equal to true? That is because during our gradient descent learning phase, we will be updating our m and b depending on their derivatives with respect to whatever output that we calculate. Okay, so we say self.b is equal to torch.tensor, and this is also going to be 0. D type is equal to torch.float 32, and requires grad, we set this also to true. Okay, so at this point we have our constructor created. The next thing we are going to define is a method called predict, which we can call and give it any value for it to make a prediction on using the parameters. So in this case, the parameters of our linear model, the parameters of our linear regression model are m and b. Okay, so I also mentioned in the previous video that there is a way of telling PyTorch not to track the transformations you are performing with some of the tensors which requires grad, because these are sometimes you want to perform some calculations but you don't want them to affect the gradient calculations, and in that case PyTorch gives us a context that we can set to tell PyTorch to stop tracking gradient for just that particular block of code. And the way to do that is you say with torch dot no grad. So what this does is that it's telling PyTorch that, hey, indeed we have set our parameters m and b to require gradient, but for this particular call we don't want you to track the transformations that are performed on it. In essence, we don't want the gradient calculations to be affected by whatever we do in this block. Okay, so over here we're just going to do return, and then we are going to do self.m times x, and then we are going to do plus self.b. Okay, so you feed in some value x, and then what the predict function is going to do is going to apply the current value of our m and b parameters in the linear relationship, and then it will come up with the value. Now, because this is going to return one item, I mean, we are creating this predict function with the expectation that callers will only pass numbers, like scalar numbers to it, not vectors for starters. So because of that, we are going to call .item. And if you don't know why we are calling .item, it is because for every tensor that has one item, you can call the .item method to return just that value contained in the tensor. Okay, the next thing we want to do is, because we have started off with our parameters set to 0, which is not the true parameters that are representing the relationship in the data set that we've created up here, we need to find a way of calculating the error. And I have explained this several times, that in gradient descent, you need a way to evaluate how far off your model is from the ground truth. For linear regression, the common error function that we use is known as the mean squared error. So we are going to create a mean squared error over here. So I'm going to call it def MSE to stand for mean squared error. And this is going to take the true y values, and then we are also going to take the predicted y values. And the formula for the mean squared error is very simple. You just take the difference between the true values and the predicted values, you square them, and you calculate the average. So it's going to give you a fair idea of how wrong our model is as far as its predictions on the given input are concerned, compared to the true values that you expect it to produce. And it is this value that will back propagate to calculate our gradient and then update our parameters. So over here, I'm going to return y true minus y predict, and then we're going to square it, and then we call dot mean. Once again, you are seeing how similar the PyTorch APIs are to the NumPy API. At this point, you might not even be able to tell whether it is PyTorch or it is NumPy, but of course it is PyTorch because we are making use of our parameters that are tensors created using PyTorch. Okay, so now we have our mean squared error created. The next thing is to create a function we can call to actually train our model. And so I'm going to call def, I'll call it train, and it's going to take the self parameter, x, the y. So you have to give it the x, the independent variables, and the dependent variables, which is your true y values. And we're also going to specify a learning rate. I'm going to assume 0.001 by default. And I'm going to set a number of epochs by default to 3000. I mean, you can always override it when you are calling the train function. As always, let's create a list that is going to keep track of our losses, because that is one way for us to verify if the gradient descent algorithm is working properly or not. And if it is working properly, we expect that our loss will continuously point downwards. It is going to reduce up until the point where it plateaus at 0, okay, or near 0. It's not always going to be 0. Okay, so for that number of epochs, so I'm going to say for epoch in range, I'm going to start from 1 to epochs. And because I'm starting from 1, I'm going to add 1 to the epochs that have been set, because ideally by default it starts from 0, but I want my output or feedback from the neural network to actually start printing from epoch 1. It doesn't make sense to see epoch 0. Okay, all right, so with this done, the next thing we do is let's make a prediction called y predict on all the values in the x vector. And so it is going to be similar to what we have in our predict function, but without the torch.nograd context block. And the reason is that for this particular transformation, we want PyTorch to keep track because it is from this calculation that we will evaluate our gradient, and then we use the gradient to update the models to point it in the downhill direction. If you haven't watched the video on gradient descent, then you have to watch it before everything else is going to make sense to you. At this point, I don't want to repeat myself by saying what have been said over and over. It gets boring. Okay, so now we have our y predict. So basically we have fed in some x values and their corresponding y values, and we have used our current values, whatever has been set for our current parameters m and b, to come up with a prediction, y predict. As you can imagine, because our m and b have both been set to 0, you can see that the model is basically going to return 0 for all the y predict. And so we need a way to evaluate our error or the loss that we are making. And to do that, we are going to call our MSE function, because we've already defined how to calculate the mean squared error up here. So we're going to say loss is equal to self.mse, and then we're going to pass in our true y, and then we are going to pass in the y predict, the predictions that the model is making as per the current values set for its parameters m and b. Now we have our loss calculated. Mind you, the loss is going to be a tensor with just one value, because we take the mean of the difference, the mean of the squared of the difference between two vectors. So it's going to be a scalar number at any time you call it. And because it is a tensor with just one item, we can call the dot item method to retrieve the floating point number which represent our true loss and append it to our losses. So I'll say losses.append, and then I'll call loss.item on it. Okay, now we want to give an output. We want to show progress information during training. It's boring if you are training for 3,000 epochs and you're not seeing any information, you're not getting any feedback from your neural network or from your model. So, and you also don't want to give feedback on every epoch, because it's not too useful. So what we're going to do is we're going to print a feedback after every 100 run of training. Okay, after every 100 epoch, we are going to give an output, so that you have a feedback from the neural network to see whether your gradient descent algorithm is working or not. And because the way to see if gradient descent is working is to observe that your loss is pointing downhill, we are going to print the loss over here. So I'll say if epoch mod 100 is equal to 0. So after every 100 epoch, then I'm going to print epoch, and then I'll say this epoch of, so basically I won't say epoch 1 of 3,000, epoch 200 of 3,000, epoch 300 of 3,000, stuff like that. So I'm going to say epochs over here, and then I'll print the current loss value. And so I'm going to put loss here, and because I'm using loss down here, I have to come here and say loss is equal to okay, so we already have loss here, and so I can call loss.item just as we have done over here. So I'll just say loss.item. I wanted a way to not have to call item twice, but it's fine. So yes, at this point, this is when things get interesting. So this is where we want to call backward on our loss value. Okay, and once we call backwards on the loss value, PyTorch is going to calculate the gradient of our parameters m and b with respect to our loss. Because the partial derivative of the loss with respect to m is an indication of how the loss is going to change when you change m by a small number. In the same way, the partial derivative of the loss with respect to our parameter b is telling us in which direction our loss is going to point when we nudge the b parameter by a little value. And that is all we require in gradient descent to actually learn. So what you do here is you call loss.backward, And at this point, you want to tell PyTorch not to track gradient, and I will explain why. So you say with torch.nograd, what you do now is you say self.m is equal to self.m minus learning rate times self.m.grad, and I explained this in the previous video. So is equal to learning rate times self.b.grad. So basically we are getting the partial derivative of our parameters m and b with respect to the loss, and then we are using that to update the parameters. That is basically how the gradient descent algorithm works, and that is exactly what we are doing here. The reason why we are telling PyTorch not to track gradient for this particular block is, you see, we have set requires grad to true for both the parameters m and b. If we don't turn off tracking of the calculations, then this line here and this line here are both going to affect the calculation of the gradient, because PyTorch is tracking every computation that you make with a tensor that requires grad to be true. So we are telling PyTorch that for this block, when we are actually updating our parameters, we don't want you to track it so it affects the gradient, because updating the parameters has absolutely shouldn't have a bearing on what our neural network did in terms of all the transformations that it went through before evaluating the loss. So that is the whole idea. Okay, now the next important thing you have to do is to also zero out the gradient for both the m and b parameters, because in PyTorch gradient calculations are accumulated. So if you don't zero it out, the gradient that you get for one epoch is going to affect the gradient for the next epoch and the next and the next until your training is done, which is actually going to make your gradient descent implementation very wrong. These fine details are the reasons why I chose PyTorch for this course. We can do the same thing with Keras, but Keras has a high level API that appeals to people, and I'm not talking down on Keras. I use Keras, I love it, but the focus of this course, once again, I'm going to remind you, is about understanding how deep learning actually works. That is why I want you to have this fine-grained experience and knowledge at your fingertips, and so we are doing everything manually for you to see how it actually works. Okay, I mean, you should be thankful because we could have used NumPy, and NumPy wouldn't calculate gradient for us, so we have to actually learn calculus and then evaluate the gradient. So PyTorch at least is saving us by giving us the orthograd feature. Okay, so let's zero out. So you call m.grad.data.0, and we are zeroing out in place, and then you see self.b.grad.data.0, which is also zeroing out the gradient for our parameters. Okay, at this point, let's return our losses and let's see what happens. Okay, so we have implemented our nice looking linear regression model. Let's come and make use of it down here. So I'm going to create an instance of it. Let me call it regressor. Regressor is equal to linear regression. Okay, and then I'm going to say losses is equal to regressor dot train, and for training I'm going to give it x and y, which are values that we have already created here. So the whole idea is, after training, we expect that our linear regression model will produce m and b values that are close to 9/5, which is also 1.8, and then 32. At that point, we know that our implementation is working and our regressor has actually learned the linear relationship between the dependent and independent values that we are giving it. So let's see what happens here. Okay, good enough. So you can see that the loss started at 688 and it came to 461 and 309 and 207, and it has come all the way to 0.0063 blah 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 after the 3000 epoch. So this is an indication of the fact that our linear regression model is actually working well, and our implementation of the gradient descent using backpropagation is working as expected. Like always, you have to plot your learning curve, and your learning curve is basically your loss versus the epochs. So I'm going to say plt.plot our losses, and we expect to see a smooth curve that point downhill as the number of epochs increase. Okay, at this point, let's print out what the linear regression model has learned for the value of m and b with regards to the relationship that exists in the training data. So to do that, let's say regressor, let's print regressor dot m dot item. We want to know what's in our m, and then let's do regressor dot b dot item. Let's see what it learned for both of them, and see, it learned that our m is 1.799, which is very close to 1.8 because 9 divided by 5 is 1.8. So our m here was 1.8 and our b was 32. And let's see what our model has learned. So the model has learned that our m is 1.799, which rounds off to 1.8, and then our b is actually 31.92 blah blah blah, which also rounds off to 32. So you can see that our model has learned well. Now let me tell you what is the relationship between x and y. I told you we are going to create an artificial data, and indeed we did. But what I actually did was to create data sets to represent the conversion between temperatures from degree Celsius to degree Fahrenheit. And the formula for converting from Celsius to Fahrenheit is you multiply your Celsius by this, values here, and then you get the temperature in Fahrenheit. Okay, so let's try it out. Let's Google 100 degrees Celsius in Fahrenheit. Google is telling us that 100 degrees Celsius in Fahrenheit is 212. Let's see what our model predicts for us. So let's come here, and then let's do regressor.predict. So let's predict the Fahrenheit value for 100 degrees Celsius, and you can see that we get 211.89, which rounds off to 212, just as Google is telling us. Now see, the beauty about deep learning or machine learning in general is that you don't need an exhaustive list of data points to train the model. As you can see, our model only saw temperatures in degrees Celsius that ranges from -20 to 20. It never saw the values for converting 100 degrees Celsius to Fahrenheit. However, because this small data set here was enough for it to capture the pattern, the model has learned automatically that the way to convert from Celsius to Fahrenheit is to use this formula. So you see, deep learning becomes useful when you know what you want, but you don't know how to explicitly spell out the programming statements that are needed for the model. For your program to produce whatever output you're expecting. Because as a matter of fact, if we had a data set for all the possible values of temperatures in Celsius and all the possible values of temperatures in Fahrenheit, then we don't need a model. Of course, in this case, we actually do not need a model because we have a formula for converting, so we don't need a model. But this is to prove that models are able to learn hidden patterns in your training data without you explicitly having to teach it. So you can see that there is no point here where I told the model that to convert, it doesn't even know that it is converting from Celsius to Fahrenheit. And I didn't have to hard code the formula in there. We just used the gradient descent algorithm and the model has been able to figure out the hidden pattern between the dependent values, which are the temperatures in Fahrenheit, and the independent values, which are the temperatures in degrees Celsius. So let's see. Let's try to convert 0 degrees Celsius to Fahrenheit is 32. Let's see what our model produces for us. So I'll come down here and I'm going to call this on 0 degrees Celsius, and let's see what we get. We get 31.92. If you round it off, you are getting your 32. So our linear regression model here is very good. It is not too wrong, and you can play with it. You can train it for longer epochs to see if it is going to improve, if it is ever going to get to 32, or if it's ever going to go above it. I mean, let's see what happens if we train it for fewer epochs. Okay, so in our definition of train, epochs was set by default to 3000. Let's set it to, let's say, 1000. So epochs is equal to 1000. And let's see what happens if we train for just 1000 epochs. So at 1000 epoch, you can see that it is making a relatively high loss, and so it doesn't make sense to use this model because it hasn't finished learning. You can see that it is still trying to learn at with a loss of 18.86. You are not very close to what you are looking for. So you can see that it has almost finished figuring out the gradient, which is the M, but then it still has some work to do to figure out the intercept on the y-axis, which is our B. So if we use it to convert, you can see that this is quite very wrong from what we expect. So this should let you know that sometimes you have to train for longer epochs for the model to actually make adjustment up until the point where it is able to figure out what you want it to do. So I have trained it for 7,000 epochs, and now you can see that the loss is very, very low, like 0.00000002 blah blah blah. So that is very low, and that should get us very, very close to the correct answer. So you can see that over here we have 1.799999, which is actually 1.8, and then this is 31.999, which is actually 32. So if I do this, then you can see that at this point we have actually gotten 32, because 31.9995 is actually 32. So thank you very much for watching this video. Don't forget to leave your comments, your questions, and don't forget to subscribe if you haven't done so. It helps me to be motivated, and it helps others out there to appreciate the little effort that I'm making, contributing knowledge to the deep learning ecosystem. So I will see you in the next video.